Hey guys, so we are using the Tensor representation of stress and strain to describe the elastic behavior of material. We want to understand how much information we are able to get out of this representation. Of course, as simple as a linear relation between a cause and the effect, we are using tensor notation to make it a bit more comprehensive. And we want to know what more information or what other relevant aspects get revealed by this representation here. Because we are making it complex, we want to know what benefits we get out of it. Now, of course, we refer to this as stress or a causal agent, and this is rather the effect that we observe in the material. Now, as things stand, when you consider this representation of this elastic behavior, what we essentially find is, of course, the stress and strain, which are supposed to be a square matrix represented as a square matrix, are now written as a column matrix. And this was possible thanks to Axel Voigt. We use this Voigt notation, and because of this Voigt's notation, we are able to express the tensor form of this on a piece of paper in a two-dimensional surface. Now, if you consider this expression here, particularly when you want to understand the effect of this normal stress, what we essentially observe is, in addition to that of the normal strain, so we have a normal stress that gets imposed. In addition to that of the normal strain, we also have some shear strain that is introduced by this normal stress. The amount of shear strain depends on these entries here. So you have a normal stress that is going to cause us a shear strain. Now, ideally, when we consider a crystal system like this, wherein my crystallographic angles, the angles that are here, we call those as a crystallographic angles, the angles between my frames of reference, when they are 90 degrees, no shear stress will be caused by the normal stress. Because if I want to resolve my normal stress to the surface of my material, because my surface is 90 degrees, so when I resolve it, I get no components of stress, so that means there is not going to be any shear strain. But still, in this representation, I see that my normal stress is going to give me a non-zero shear strain. Now, that is possible only when my crystallographic angles, they are not 90 degrees, so when they are not orthogonal. So when they are not equal to 90 degrees, so it means I will be able to resolve my so-called normal stress into shear components, and that is going to give me some shear strains as well. So what it helps me understand is, when I have such a description for the mechanical behavior of material, if this is the way I'm going to relate my stress to that of my strain, in addition to the linear relation that we see in this primitive representation, in addition to this linear description, when I write it in this way, besides the linear relation, I'm also able to notice that my normal stress is going to give me a shear strain. So it means my crystallographic angles are not 90 degrees. So ultimately, I can say the material that I'm dealing with is a triclinic material. So it gives me a lot of information, starting from how I'm able to achieve the non-zero shear strain from that of a normal stress, ultimately leading up to what sort of crystalline material I'm dealing with. So when I'm able to expand the representation that is as simple as this using my tensor notation, it helps me understand what sort of material I'm dealing with. Now, all this understanding stems from this tensor matrix here, or rather the stiffness matrix here. So more complex or more non-zero terms that are involved in my stiffness matrix, more will be non-zero strain here. Now, if I just consider this row, if all these entries are non-zero, only then there will be non-zero shear strain. And when there is non-zero shear strain, only then I will be able to assure that this is my triclinic structure. So my understanding of what sort of material I'm dealing with stems from my stiffness matrix here. And that makes sense because while the mechanical load that I impose is described by this matrix, and the response offered by the material is described by this matrix here, that is column matrix here, this matrix, the stiffness matrix, talks about the nature of the material, and correspondingly, depending on the nature of its entries, I will be able to state what sort of material I'm dealing with. So when I'm changing the material, when I'm moving away from the triclinic, what it means is that these entries are now going to assume a different values. and depending on how rigorous or how many non-zero values are there, then based on that I will be able to classify what sort of material I'm dealing with. Now it is vital to note that in this representation, it is vital to note that it could rather be differentiated into 4 quadrants, and this quadrant deals with primarily the normal strain. So this quadrant here, it deals with the relation between the normal stress and the normal strain, and this relation, it essentially stems from the Poisson's effect. If I have one normal stress and I have 2 normal strains in the perpendicular direction, this is attributed to the Poisson's effect. So this essentially deals with the what we refer to as the effect of the normal stress, and correspondingly this quadrant here, it deals with the effect of the shear stress. Now if I move away from my triclinic crystal system to that of another crystal system wherein there are 2 crystallographic angles that are 90 degrees. So what it essentially means is my normal stress is now going to introduce shear strain in only one plane, not in other planes, because there are 2 planes that are perpendicular to one another. So I'm moving from the triclinic crystal structure wherein all my crystallographic angles are not 90 degrees to a different crystal structure wherein 2 of my angles are 90 degrees. So it essentially means that I'm chasing a different material, I'm choosing to describe a behavior of a different material, and the characteristic feature of the material is the normal stress is now going to give non-zero shear strain in only one plane. In all the rest of the planes, my shear strain is going to be 0. Now that behavior I would be able to introduce in this expression when I turn certain components of this matrix here to 0. I've changed my material. This category of material has 2 crystallographic angles 90 degree. So it means my normal stress is now going to give me 2 zero shear strains. There are 2 shear strains that are going to be 0. Only one non-zero shear strain is going to pop up. Now such a material, we refer to it as monoclinic. Now behavior of such a monoclinic material I will be able to introduce in this representation when I change the entries of these matrix, certain entries of this matrix to 0. For instance, if I consider these entries to be 0, then I could very well observe that this normal stress that I am imposing, of course, is going to give me all the components of normal strain and only one component of shear strain, and the rest of these is going to be 0 because these 2 entries are 0. So my matrix here, it essentially represents the nature of my material, and because these entries are 0, it is reflective of my crystallographic angles 90 degrees. So ultimately I will not be having shear strains in that plane, so this will become 0. So when I reduce the number of non-zero entries in my stiffness matrix, correspondingly what I'm doing is I'm changing my crystal structure. I'm reducing the complexity of my crystal structure. Initially all my entries were non-zero, so at that time I was dealing with triclinic. Now only one of my crystallographic angle is 90 degrees or non-90 degrees, so now I'm dealing with monoclinic. Initially triclinic, all the 3 crystallographic angles were non-orthogonal. Now I'm dealing with monoclinic, only one is non-orthogonal. So in that case, some of my entries, they turn to 0. Correspondingly, my normal stress that I'm imposing is giving me only one shear strain and 2 other shear strain turn to 0. Now the reason we have these different entries here is because we discussed in the previous lecture, it talks about the anisotropy of my material. So the same load is going to give me different effect in different direction. These different effects in different directions are quantified by these entries. So when you have too many non-zero entries in my stiffness matrix, so we have highly anisotropic material. And if you have a varying values in my entries, so each of these values are different, it means in each of these directions my effect is going to be different, so it means I have a highly anisotropic material. When my complexity of, the so-called complexity of my crystal structure keeps on reducing from triclinic, if I move to monoclinic, then the number of 0 entries, the null values, the 0 entries in my matrix keeps on increasing. As I move from triclinic to monoclinic, these here, they turn to 0, indicating that my normal stress is now ultimately going to give one shear strain alone. Now, of course, we have written all these things in, or particularly our shear, or rather our stress and our strain in the form of a column matrix. So ultimately, we don't really need such a representation. We can write it in this way as well. So because we are now treating our stresses not as a square matrix but as a column matrix, so we can rewrite it in this way. So the entire discussions become much more easier. So what we applied for stress, we can also apply for strain, and correspondingly our 4 indexed components of the shear or the stiffness matrix now becomes 2 indexed components. Now again, what we have so far done is we are considering monoclinic. So in the monoclinic, these terms become 0 because my normal stress is only going to give me normal strain plus 1 shear strain because one of the crystallographic angles is non-90 degrees. Now if I consider a case wherein all my crystallographic angles are 90 degrees, then ultimately I would end up with such a stiffness matrix because my normal stress is only going to give me normal strains. So all these strains are normal strains and all these turn to 0. So we started off with triclinic, we moved to monoclinic. If now I am talking about a crystal structure where all my crystallographic angles are 90 degrees. So in that case, my normal stress is going to ultimately give me normal strains. Of course, my actual response, and also because of the Poisson's effect, I'm going to have 3 normal strains, but there is not going to be any shear components. So this representation talks about a crystal system wherein all the crystallographic angles are 90 degrees. Now, on top of it, there is also one other understanding we need to gain here. That is, if I consider this stress here, the effect of this stress here. So all these 3 stresses, they talk about the normal stresses, and all the 3 remaining, they talk about the shear stresses. So if these 3 talk about the normal stress, these 3 talk about the shear stress. Now if I want to consider the effect of the shear stress, all I need to do is multiply this to that of this column here. I have to multiply this to that of this column here. All these terms are 0. So if I have to, all I have to do is mirror this portion of my matrix here. So all these columns is 0. So what I see is my shear stress is causing a shear strain. My shear stress is causing shear strain epsilon 4, epsilon 5 and epsilon 6. But it is vital to note that my sigma 1 can cause epsilon 1, epsilon 2 and epsilon 3 because these stems from Poisson's effect. My sigma 1, my normal stress, can cause normal strain in 2 directions because of my Poisson's effect. But the same cannot be expected of my shear stress 4. It cannot cause any strain on these 2 because Poisson's effect is not active for the stress that is acting on the surface. Poisson's effect is active for the normal stress. Poisson's effect is not active for the shear stress. If I take that understanding into consideration, then an accurate representation for a crystal satisfying this condition would be of this form here. So even these terms, which were originally non-zero because we were just considering the effect of normal stresses on the strain, now when we begin to consider the shear stress, even these terms, they turn to 0 because the shear strain, that is 4, 5 and 6, they have no Poisson's effect. So ultimately what they would end up giving is, they will end up giving us the corresponding strain of epsilon 4, epsilon 5 and epsilon 6. Again, this lack of Poisson's effect in combination with the orthogonality between the crystallographic axis gives us such a stiffness tensor. Now of course I can write this as, I can complete all these entries and this is how it would look like. When you have a condition where all the crystallographic angles are 90 degrees, and there is, of course, as we have understood previous, or as per the understanding that the shear components of stresses will not introduce any Poisson's effect, and of course the normal components of the stresses introduce Poisson's effect. With that understanding, and for this crystal system wherein the angles are 90 degrees, the mechanical behavior is expressed in this way, wherein your normal stresses, they contribute to your normal strain but no shear strain. Your shear stresses will contribute to your specific shear stress. Now ultimately what now you observe is the number of non-zero entries have significantly reduced, or to put it another way, number of zero entries in the stiffness matrix are significantly increased. So as we move or as we reduce the complexity of the crystal structure we are considering, it gets reflected in the way we are describing our stiffness matrix. The more zeros that you see in your stiffness matrix, the more easier is or more straightforward is your crystal structure. When you have a complex crystal structure, of course the term complex is heuristic here, meaning we are talking about in the range of crystal structures, the most complicated one, we will have all non-zero entries in the stiffness matrix. So that relates to our triclinic. And as we move and as we reduce the complexity by changing our angles, the crystallographic angles, or making them 90 degrees, then you observe that significant entries of the stiffness matrix turn to zero. Now it is also possible for us to even simplify this. Now again, each of these entries, like we discussed, talk about anisotropy. So the more non-identical entries we have, it's no longer about it's not about zeros and non-zeros. Now it's about how different each of these entries are. So the more non-identical entries you have, it means you are going to observe different effects in different directions. So more anisotropic is your system. Again, now we have moved away from that of triclinic to monoclinic to that of an orthogonal systems. Even in this orthogonal system, there exists anisotropy primarily because each of these entries are different. So more different your entries are, the more different is or more anisotropic is your material is going to be, because for a given normal stress, you are going to observe 3 different types of shear strains in 3 different directions. It's not, the magnitude is not going to be the same because these entries are different. So essentially then what we observe is more non-identical entries in our stiffness tensor. It means more anisotropic is your material. Even you can be talking about the same crystal structure wherein all the crystallographic axes are orthogonal to one another. Even in such a system, the disparity between different elements or different metals, assuming such a crystal system, will be based on the values of these entries. When these values are significantly different, your system is more anisotropic. When there is an overlap, there is a similarity, then your system becomes isotropic. Now we can consider one condition wherein there is a difference between the response of the material to the load in this direction, that is vertical, and that of the horizontal. So the only disparity is between vertical and horizontal. We are not now making a disparity between each of these directions. We are assuming that the effect in these 2 directions, if this is 1, 2 and 3, let us assume that the effect in 2 and 3 are equal, but when compared to that of 1, they are different. So the effect in 2 and 3 is equal but different from that of 1. We are going to consider such a case wherein the effect in 2 and 3, the strain that is introduced in direction 2 and 3 because of a stress in 1 is equal to one another, but it's different from 1. So if I have a stress, a normal stress that's causing strain, 2 of these strains, 2 and 3, are equal but not equal to that of 1. If you consider such a case, what it means is such a condition can only be introduced when I appropriately change. So such a behavior, I see a material which is anisotropic, but it is not anisotropic in all the 3 directions. It is anisotropic in only 2 directions, that is vertical and horizontal. In the horizontal, it is isotropic, vertically it is anisotropic. So vertically and horizontally, if I consider, there is a difference. But all that I am considering is horizontal. If I am considering just the directions 2 and 3, it is an isotropic. But when I consider 2 or 3 with respect to y1, it is anisotropic. So if I consider such a case, if I consider such a material, then essentially the description of that material will be introduced in this expression when I am appropriately changing my entries. Now when I do that, I end up having such a relation, such a description of my stiffness tensor, wherein I see that these 2 are equal. These 2 entries are equal. So essentially I am made of the 3 distinct entries. So I had C11, C12 and C13, and I had C23. So these 2 are now equal. So this is normal component and these 3 are the shear component or the component that move away from the normal axis. So I have 1, 2, 2, 3 and 2, 3 and 3, 1. When I say these 2 are equal, I'm distinguishing, or I'm treating this as the one responsible for the horizontal plane, and this contributes to the vertical plane. So this is totally different from these two. So when I make this assumption, I'm able to rewrite it in this form. And of course, under this condition, my shear component will also vary like this. So of course, we don't want to get into the derivation of it, but what we have to understand is, when my degree of anisotropy decreases, so what I'm essentially doing is, instead of having different effects in different directions, instead of having different effects in 1, 2 and 3 direction, I'm assuming that my effect in 2 and 3 are the same but different from that of 1. If I have such a material, such a crystalline metal, what I'm essentially having is a material that is relatively less anisotropic to that of a material wherein in all the directions the effects are different. So in such a case, the way my stiffness matrix changes is the number of non-identical entries becomes reduced. So in this case, I have too many identical entries, so it means my material, or the material that is getting described by this stiffness matrix here, is relatively less anisotropic. So there are two aspects of a stiffness matrix that helps us understand the nature of my material. One is how many non-zero entries I have. When I have an increased amount of non-zero entry, it means I'm dealing with relatively a complex crystal systems. The second question is how many identical entries I have. When I have a greater number of identical entries, it means I'm dealing with a less anisotropic system. When all the entries are significantly different, I'm dealing with an anisotropic system, a more anisotropic system. So this matrix here, it tells me quantify, it helps me get an understanding of the nature of my crystal structure and how much anisotropic is my system is. And depending on how many non-identical entries, or we refer to them as independent entries, because these are independent, they are non-identical. Depending on independent entries, I will be able to state what sort of crystal structure are they and how much or what degree of anisotropy they expose. So of course the anisotropy can be related to that of the crystal structure. So ultimately from this, I will be, depending on how many independent entries I have, I will be able to say what is the crystal structure that I am dealing with. So all that I am dealing with is a cubic crystal structure, then of course this holds true. If I am dealing with cubic crystal structure, this holds true, because in my cubic crystal structure, all the crystallographic angles are 90 degrees. So these entries are going to assume a zero value. They are going to be trivial ones. And depending on how my anisotropy is, these entries are going to exhibit a different value. Now I guess if I count the number of independent entries here, so this will be my 1, this will be my 2, this will be my 3, and this will be my 4, and then this will be my 5. Okay, so yeah, this will be my 5. So ultimately I now have 5 independent entries, and that describing my cubic system, because now I have all my angles to be equal to 90 degrees, and I've assumed that my vertical is different from that of the normal. So what we essentially have observed here is the descriptive expression of my tensile behavior using tensor notation. It helps me describe the mechanical behavior. In addition to that, it gives me information on what sort of crystal I'm dealing with, what sort of crystalline material I'm dealing with. It helps me understand what is the nature of the crystal structure and how much anisotropy it is. Now, when I'm rather able to tailor this stiffness matrix here through appropriate processing, when I'm able to tailor this matrix here, then correspondingly I will be able to achieve that degree of anisotropy or isotropy in my material. If through certain processing technique, if I'm able to achieve identical values of these entries, if I'm able to reduce some non-zero entries to 0 through certain processing techniques, so essentially what it means is I'm able to rather increase or decrease the anisotropy. I'm essentially changing the crystal structure of my material. And when you see a textured material, when you see a material with a specific crystallographic orientation, when you see that is a material is isotropic, when you see a less anisotropic, all that can be described using this matrix here. The different behavior of materials. When you have a tensor notation, the different behavior of materials, be it high and highly anisotropic, less anisotropic, isotropic, all this can be described by this. And once when you have this expression here clearly laid down for you, then when based on how it is laid out, you will be able to say what sort of material it is and what sort of crystal structure at least it is, and how much or what is the degree of anisotropy that you can expect out of such a material. So which is quite remarkable, because all this information we are able to gain from one entry here. So with this discussion, we will be winding out our course on mechanical or mathematical techniques in materials research. And possibly there might be one or two auxiliary lectures, but I hope that you are able to appreciate the amount of information that we will be able to introduce when we express this simple relation using tensor notation. Take care, guys. Goodbye.